This video goes over 1D kinematics, i.e. motion in a straight line. I will show you how to use the definition of position, velocity, and acceleration to solve pretty much any 1D kinematic problem. It also shows you how to explore those equations that you probably are forced to memorize in your physics courses. Let's get started. I'm going to begin with a few assumptions of your understanding of 1D kinematics. This is the number line. We're going to talk about motions purely along the x direction. If the object is to the right of x equals 0, it's in the positive location. If it's to the left, it's in the negative location. In addition, if it's moving to the right, the object is moving in the positive velocity direction. If it's moving to the left, it's moving in the negative velocity direction. So we begin with the definition of velocity given our understanding of position. Velocity at some period of time is the time rate of change of position. Since position can change with time, velocity can also change with time. I'm going to put a sub x to remind me that this is velocity purely along the x direction. This expression tells me that I can find the velocity of the object at some point in time if I know the rate of change of its position at that time. What about in the other direction? What if I want to find the position as a function of time, knowing the fact that I may have the velocity as a function of time? Well, we have to give it some initial conditions, that at time t equals t sub 0, that it's at some location. If we do the desolve command, we find that, not surprisingly, position is the integral of velocity. At this point, allow me to introduce the idea of momentum. Momentum for an object that possesses mass simply means weighted velocity. So therefore, if an object is moving to the right, its momentum is to the right. It's positive. If the object's moving to the left, its momentum is to the left. It's negative. The definition of momentum for an object that possesses mass is mass times its velocity divided by this factor. This factor involves the speed of light, c. Light travels at tremendous speed. Therefore, this value is large because even if you square it, it's even larger. Most courses do not include this factor because it's too difficult for the students to understand. Fortunately, we have Maple. What you're likely to learn is that momentum is defined as mass times velocity, weighted velocity. And that's fine because this factor is generally on the order of 1. If we solve this expression for velocity, we find that the velocity is in terms of this expression. Consequently, momentum as a function of time can be calculated from this rate equation. Given the velocity and momentum is related to the time rate of change of position, what is the time rate of change of velocity? We call that acceleration. So here's the definition of acceleration mathematically. As before, if we define acceleration this way, and we provide an initial value for this velocity at time t equals t sub 0, we can solve for the expression of velocity as a function of time in terms of acceleration. This one allows us to go from velocity to acceleration. This one allows us to go from acceleration to velocity. It should be pretty obvious. If this is the derivative, then this should be the integral. Modern mechanics has the philosophy that position is a consequence of momentum, and momentum is a consequence of a force. However, in most intro courses, the relationship is position is a consequence of velocity, which is a consequence of acceleration. Or, in other words, measuring the acceleration tells us about the velocity, given the initial conditions, and the velocity gives us information about the position. Most of the problems in 1D kinematics involve these connections. Given our definition of velocity and our definition of acceleration, and saying that we have some initial conditions for the initial position and the initial velocity, let's see how acceleration dictates what velocity and position is as a function of time. Not surprisingly, velocity is a single integral of acceleration and position is a double integral of acceleration. So what if our acceleration is a constant with time? What is the value for these velocities and positions as a function of time? Here's the expression for the velocity. Here's the expression for the position. These look pretty complicated. Most people start actually with t sub 0 equals 0. Evaluating our solutions at t sub 0 equals 0, and you get the famous expressions that you probably have to memorize. One for velocity and the other one for position, given a constant acceleration. Let's extract out each solution and make them a function, and then make an array plot which we can explore. Here is position, how it changes as a function of time, and the object's velocity as a function of time. As we change the initial position, we notice it has no effect on the velocity. If we change the initial velocity, we can see that it has an effect on both the velocity and the position. We started with a positive acceleration. What happens if we have a negative acceleration? You can see how the parabola changes. Because acceleration is constant, we know that the velocity is a straight line and the position is a parabola, either up or down. Let's try this problem again, but this time, instead of using a constant, what if our acceleration only varied with time? Let's plot. So in this one, the acceleration is basically a cosine curve. We can see again how the initial position affects x of t but has no effect on v of t. We can see how the initial velocity will have an impact on both of them. We can see how the acceleration, whether it is positive or negative, changes essentially the phase, and this affects the frequency. But now we're going to do a problem where our integral equations fail. In this particular problem, the acceleration is not just a function of time, but it is also a function of the velocity, which might be a function of time. If we hit enter, and then we try to evaluate our solutions given this acceleration, we find out we get no solutions because, not surprisingly, velocity is the integral of itself. This is where we have to go back to our initial approach and now insert the acceleration into the problem before we do d-solve. So I've now put the definition of our a sub x as a function of time back into the problem. Here's again our definition of velocity, our definition of acceleration, what our acceleration is, and the two initial conditions, one for each of the differential equations. Now we can do d-solve on these four sets of equations for the two unknowns, and we get an answer. It is a bit complicated. Let's make it even simpler by saying the initial time where we start is 0. Starting the time at 0, we recalculate, and we get somewhat simpler equations for the velocity and the position as a function of time. As before, we extract out the solutions, and we write the code to create a plot for our array and our explorer. Our initial position can affect x. Our initial velocity has an effect on x and y, and also a, because a is a function of its velocity. Our initial a could be 0, therefore things aren't going to be interesting, or it could be positive, and the alpha factor can change how much the velocity changes. So we return to our general solution, using the definition of velocity, using the definition of acceleration, defining what the acceleration is as a function of time, position, and velocity, and providing the initial conditions, you can get a general solution for the position and the velocity as a function of time. If it's mathematically impossible to find a closed form solution, you have to do it numerically. The document associated with this video goes over the details more carefully and provides more examples. In addition, there are example problems solved in another videos on these topics, some using the equations you learned in class, and some using the approach that was discussed in this video. As always, you can find more information on Gould.prof.